Yes.
Is there, at the same time, is there like a lab going on for 6?
Yes, correct.
So what we're going to cover today in the lecture, just
I'll explain that in a moment.
so I can decide what happened to
Other, yes, you're welcome to go to the lab and do coursework. Other questions? Okay, quick comment. First comment is I'm aware that Massey has posted the last coursework for this course to Moodle. It's also perhaps on his webpage. About that in a moment. Okay, plan for today. I want to do 2 things today. 3 things. First is I want to give an overview of my final coursework, the Kernel Perceptron, which I'll do initially. Then, after that, I will jump into Mathematica, finishing off Mathematica. After that, if there's time remaining, and there's currently in lab 406, well, Guanyang and Orlando will be there about 3:30. They can offer you help with the 5 coursework assignments, and likewise working on the Mathematica lab. Okay. Does that answer your question?
Yeah.
Okay. So I first want to say a few words about the final coursework from my half. Okay. Okay. Final coursework. Quick comments are as follows. It's divided into 2 parts, part 1 and part 2. Part 1 is 20% of your mark. Part 1 is a Mathematica exercise. I want to make a quick comment on it. First part of the Mathematica exercise asks you to develop a Mathematica code to count characters, to count the frequency of items in the list. That should be straightforward. The second problem is a bit more challenging. You can look at this sample input and output, but basically it's a function to remove brackets from nesting from a list in Mathematica. So for instance, in 1 we see the list A, B, C, D with all sorts of nesting. My flat removes that nesting. Part of the purpose of this exercise is to get you intimately familiar with programming using recursion. So we had a couple of examples. We had an example with factorial. We had an example with reverse. Exercise 2 should be done using essentially recursion to do this, or optionally you can use Mathematica's pattern matching features, which I'll discuss later today. So you should use for loops and while loops to do this. Okay, that's a small part of the assignment. The second part of the assignment, I think, is an interesting assignment. Well, first, from a brief, what you need. One thing which may not be immediately obvious, even though it's in the 5th part of the coursework, you're allowed on part 2, as desired, to work in a group of 2, even though part 1 should be done on your own. So you're welcome to work with somebody on this. Likewise, it's not necessary for you to do it in Mathematica. And unless you're fairly experienced in Mathematica, I actually think it's a fairly hard problem to do in Mathematica as a first larger piece of code, because it's easy to write inefficient code in Mathematica, and this coursework is computationally demanding. Okay, so what is the exercise about? Well, at a high level, it's about digit recognition. First, quick show of hands. Is there anybody in here who's not in supervised learning? Okay. For those of you who aren't in supervised learning, just quickly tell me what courses you're in. What degree you're doing? Financial? Okay, financial risk management. Okay. So this is, as with our first four courseworks, this continues to be a machine learning style exercise. However, the algorithm is straightforward. You'll find out you know very little. You'll need to know no supervised learning to do this. You'll just need to implement an algorithm. Perhaps you won't understand some of the deep things going on behind the algorithm, but it's not required to do the exercise. Just so you know. Okay. Okay. But in describing it, I'll use a bit of supervised learning language. Okay. So, a classic problem would be to perhaps recognize digits scanned in some way. So here we can see 7, 8 to 9 scanned in. These are the formatted data, which I'll get to the end. These are, I guess, 16 by 16 and perhaps 256 levels of gray. Maybe there's fewer levels of gray, but you can basically think of this as a 16 by 16 matrix or a 256 element array, which represents the digit. Your goal is to build a classifier to distinguish between different digits. How are you going to do this? Okay, for those of you in supervised learning, you've seen the Perceptron already, you've seen kernel functions. For those of you who haven't done supervised learning, you've seen the use of basis functions. The idea of using a kernel is similar to the idea of using a basis functions, but there's clear technical differences. So what we're going to do is one of the perhaps simplest algorithms in machine learning is the Perceptron algorithm, and we're simply going to add a kernel to it. The nice thing about a kernel Perceptron is it's the algorithmic description of it, as you can see, is extremely short. This is our algorithm. It's possible to implement this relatively efficiently. Nice feature that it has, though, is for this very simple algorithm, you can have comparable performance, though often not quite as good as, for instance, like an SVM with a kernel, or some other perhaps more complex machine learning algorithm, but it's extremely simple to implement, and there's various improvements to improve its performance, but I think if you experiment, you'll find that it does fairly well. It'll do fairly well most places, and SVM will do well, if perhaps not quite as well, but it's simpler. Okay. Let's understand what the algorithm how it works. The algorithm takes as input a sequence of vectors. So x1s are pattern vectors, y's are output values. Here I'm doing for 2 classes, so you can imagine that you're trying to classify a given pattern xi to its pattern yi. And essentially the way it works is we build a linear classifier in some high-dimensional space to classify the data. So how does this work? Well, our initial linear classifier is a linear classifier that's 0, in the sense that it predicts 0 no matter what input we see. And what we're going to do is we're going to build a function. Let's first describe the form of this function that we're going to build. So I'm going to write, just to familiarize you with the notation on the coursework, since some of you may be unfamiliar with this style of notation. We're going to build some linear classifier. We'll call it WT. This will be your linear classifier after the tth iteration. You'll keep improving your linear classifier on each data point you get. WT, your linear classifier, best way to think about it is as a function. Okay, I'm going to write my function notation in this format. WT is going to be equal to a linear combination of kernel functions. So for I equals 1 to t, it's going to equal alpha t, alpha I kxi dot. I want to clarify this notation because sometimes people go, what's the dot there? What's going on? What I'm doing is I'm writing a function. So if I plug in the vector r here, the way I compute the value of this function w is I do this sum alpha I k xi r alpha I. So that's what it would be, for instance, if I plugged in r. If I'm just writing a dot to mean some arbitrary value, okay, rather than a specific letter. So your function has this linear form. Now you may ask, what's k? K is a kernel. We won't mathematically say what we mean a kernel to be, but for us, the kernel is some function that's going to map Rn. We'll give it 2 arguments in Rn, and it'll map it to some number in R. So let's look at 2 sample kernels. The main kernel, which I asked you to look at in this assignment, is a kernel called the polynomial kernel, K, where K has some parameter D, and if it has arguments P and Q, where P and Q, for instance, are in Rn, then this is equal to P dot product Q to the D. If you can't recall what a dot product is, that's just the sum of I equals 1 to n, Pi times Qi. Okay, so the polynomial kernel of dimension D, where D is our parameter, which, a different kernel for each value of D, is just P dot Q to the D. Okay. Another kernel which you can choose to use for this exercise is So one of the extensions is the Gaussian kernel, where Kc of P and Q is equal to e to the minus c, the distance between P and Q squared. Okay. So the function you're learning looks like some linear combination of these functions. Okay? Questions so far? Okay. Let's look at the algorithm that learns it. Okay. The way you're going to get this linear combination, i.e. the alphas are what you're actually learning, are as follows. So the algorithm kind of works in this loop. We initialize, but then we predict, then we update, then we predict, then we update, then we predict, and then we update until we're run out of data. Okay? So the way we predict is we simply plug in our current data point xt, we plug it into our current function wt, and we take the sign of it, i.e. we round it to 1 or minus 1. And we do that by just evaluating this sum of kernel functions. Okay. Once we predict, we then update this sum to get a new term in it, which corresponds to the last point we've seen. Okay. So if we predict it correctly, in essence, we're doing nothing because we update this representation, which is a sum of kernel functions. The new kernel function has 0 as its coefficient in front of it, so it doesn't contribute anything. Okay. So if we predicted correctly, i.e. when we received xt, we predicted yt correctly, we just output a 0. If we predicted incorrectly, then we set alpha t equal to yt, and we add on, instead, with alpha t equals 0, we add in with alpha t equals whatever the value of yt is. So that's all there is to the way the algorithm works at a first description. Questions of how this works? Okay, a question you might want to ask yourself is, why do this? Why does it work? What's an intuition? Let's try to give a real informal kind of sloppy intuition about why this algorithm works. Okay, you know, one could drive quite detailed intuitions. Let's think about this kernel, Kc equals e to the Cp minus q. It's easier to have an intuition with this kernel than it is with this kernel, even though in the end they roughly do the same thing. What does this look like? E to the Cpq, if I plug in a single variable and I plot it, and let's pretend p and q are one-dimensional, it's just a Gaussian. So, for instance, if I plot k1 dot, what does the plot look like? Well, basically, here's my axis, here's 1. 1 is where the Gaussian takes its maximum value, which will be e to the minus c here, because 1 minus 1 is 0, and so this becomes 1. And then we just have a Gaussian-like shape off on either side. And imagine if this was in higher dimensions, then we have this beautiful spherical asymmetric Gaussian thing floating off. So this is what a typical kernel function might look like. So how does this help us learn a function? Well, the intuition for how it helps us learn a function is as follows. Whenever we get a data point, xt, let's say we change our function in some way, we update it. Well, what we do is we add on a kxt function. So what we're doing is, for instance, we get our first data point, we predict 0, and so we make a mistake. And so then we get alpha t is equal to yt, so it'll be 1 here. So in fact, let's say, we put a Gaussian bump right at our first data point, centered on our first data point. Okay? That's what would happen if we made a mistake. So for instance, if we got that data point again, well, we're predicting exactly like the bump value. And it kind of makes sense, because then if you get some value near the bump, you're also predicting some large value that's similar to it. Okay? So that's what happens on the first data point. Whenever you make another mistake, you're adding another bump. That's all you're doing. Maybe you find out some point over here looks like -1. So this becomes, your Gaussian becomes upside down, and you add something like that. So your whole function, you sum these together. If they're far enough away, you basically have two bumps that look like this, and they don't interfere with one another at all. So every time we get a new point for which, if we don't make a mistake, somehow our shape is already okay, and we're not adding a bump. But if our function is wrong, we're adding a bump near that point. Okay? And so we just keep adding a bump on the current data point that we get, so we hopefully classify that data point correctly. And then you can see what this parameter c does is, if we have this very narrow, the Gaussian kind of only gives information around what's there. Whereas if we make this very wide, then the Gaussian wants to spread its values further. So somehow this is like a smoothness assumption, which is beyond the scope of what I want to do today. But this is the basic motivation: is we see a new data point. If we're not predicting the right value, we add a bump in the direction of the value we want to predict, and we build a function that looks like a bunch of bumps added together. Polynomial kernel can actually tell a similar story. Okay, so this is the intuitive motivation for the perceptron. A lot more is known about this. Questions so far? Okay, so now let's keep talking about the perceptron. Okay, so you have your data set. You're going to go through it to train your perceptrons. Let's say I have some L points. I go through it. I build my function, and then maybe I'm going to test how well I predict on some new set of data points. Fine. You can do that. I think I asked you to do that. But another thing one typically does with the perceptron, as one does with many of these iterative algorithms, is you can train it for multiple epochs. Okay? Once you've put your data set through once, you've built some approximation to the training set by this sum of bumps. But by passing the data set through again, your approximation gets perhaps somewhat closer to the training set. So each time you pass through the data set, it's called an epoch. And so I discussed this rightly up here. It's basically you might put your data set through multiple times to train a better classification. Okay.
Is there usually a standard value for t that is chosen? Or
for the number of epochs? Two comments. Well, often people, there's multiple choices. One is for most kind of, if you're looking for kind of like performance guarantees on your algorithm, in terms of what is generally known, they don't often improve after one epoch. So people say one epoch is good enough. However, in practice, most of the time, it actually helps to train more. And so, I've kind of chosen an arbitrary number 3. But you can look at how the training error is going down and decide if the training error is still decreasing to decide this. But it's implicitly some parameter which you can tune via cross-validation or some other thing, but most people just choose a small arbitrary value. But yes. So then the other answer would be, is there's also some more clever variations that we can make on the perceptron that are still fairly simple, that kind of help answer that type of question you're asking, but I don't want to go there. I want to present the algorithm in its simplest, cleanest form, which still pulls out pretty good performance. Other questions? Okay. Okay, so putting things together for a moment. I ask you to do digit classification. So these digits look like essentially 256 element vectors from the data file. And so what you'll be doing is you'll be taking one of these vectors, putting it in P. One of those vectors will form one of your arguments, and you'll use the digit data which you'll read from a file in conjunction with this. One reason to not start this at the last minute. Another side to this assignment was I'm trying to. You may not like me for it. I'm trying to make it closer to realistic machine learning, in the sense the final data set size is not a toy data set. It's not a small data set. So it's a large data set. And this is the common thing when you actually do machine learning. Your data sets are fairly large. Your code, how you code it, the efficiency will make a big deal. If for no other reason, it's going to be how fast it runs until you get some sort of output and you can assess whether your code has a mistake in it or not. Okay, so please start on it somewhat early, just so you can test your code, since your code is potentially going to run slowly on such large data sets. Because the final data set size I'm going to ask you to look at is there's some 7,000 digits, so there's roughly 700 in each class. In my experience, people write code that can go from under 5 seconds to do a single epoch of training to code that takes 4 hours or more to do a single epoch of training. So there's a real range of efficiency that's possible in one's code. Okay. Let's continue. So I discussed the kernel, I discussed training. Testing is similar to what you've done before, but you just test like you did in assignment 2. I guess you've done it on almost all your assignments. You've tested your classifier predictor on the test set. Another thing I'm going to ask you to do is, this is a 2-class learner, but it's perhaps more interesting to be able to not tell 1s from 3s, but be able to make a prediction for, is a digit in class, is it a 0, is it a 1, is it a 2, is it a 3? Many ways of generalizing 2-class algorithms to multi-class algorithms. I'm not at all saying that this is the best way, it's just relatively simple to describe. So you have this 2-class algorithm, but you want to generalize it to k classes, which will be the 10 class problem. Okay, so basically, if you look at this kernel perceptron, for instance, think about the Gaussian. You're learning this thing which is a sum of bumps. When you get a value for a given point, we say predict the label by predicting the sign, because you're going to be rounding some real number to 1 or minus 1, depending what direction it's going. You can, if that number is like close to 0, like 0.01, or somehow you're not confident in that prediction. Whereas if the number is near 1, for instance, you're quite confident in it. Okay. So to do k classes, what you'll do is you'll create a classifier that recognizes 1 versus other digits. You'll create a classifier that recognizes 2 versus other digits. You'll create a classifier that recognizes 9 versus other digits. Okay, so the way you train one of a given one classifier is you put your 1 examples in the training set, and you put your non-1 examples, 2s, 3s, 4s, also in the training set. You train that up, that gives you a classifier for 1s. And you do that across. Then when you get a new example, you look at how each of these classifiers votes. Whichever one gives you the largest value in magnitude, you'll choose that for your label. Okay, so somehow you're going with the most confident prediction that's described here. Other things you could try. Common issue in learning is choosing parameters. For this problem, there's only actually one parameter. I tell you that the number of epochs to keep it arbitrarily fixed at 3. The kernel I ask you to use is the polynomial kernel, where d corresponds to the degree of polynomials. So d could be 1, d could be 2, d could be 3, and so forth. When you do model selection, I ask you simply to vary d over a range of integers. And the way you're going to decide which parameter you're going to use is you're going to have a training set. You're going to take 2/3 of your training set, train your classifier, measure its performance on the remaining 1/3, and you'll do that separately for each value of d. And then you'll see which of these does the best, or you'll use some other method to decide to vote which d would be the best to use. And then you'll go ahead and you'll report your performance on the testing set. Okay. Okay. Finally, I just two remaining comments. So if you go to my home page, you'll find files for the experiment. The files you'll find for the experiment are the following. So I'm either good or I'm either bad. I give you some demonstration code in Mathematica for this problem. So I went ahead and I coded up something that does it, so you can kind of see how the kernel perceptron is supposed to work in Mathematica. However, I wasn't completely good in that the code kind of has a very inefficient design built in. So you can't really work with my code. You can use it to get a feel for what's going on, but if you try to copy its logic exactly, you'll end up writing inefficient code. I think I literally do what the algorithm is that I say here, but if you really want to write efficient code, you kind of have to think about how to make my code more efficient, what's causing inefficiencies. So I have sample code here, but and it should follow the algorithm described there, but it's not an efficient way to do it, either algorithmically exactly. There's better data structures that you might use to implement things, and the Mathematica, there's probably more ways to pull out more performance in Mathematica. But it gives you a basic flavor of what's going on if you don't understand what's clear and unclear. Okay. Okay, so for this assignment, so remember on the second part, you can work with another person as desired. You should produce a report, basically how you chose the parameters. I'll look at your final test error scores. It should certainly be under 9%. It should be clear. I just then I list some things which should be in this report. One is how you implement this sum. There's more or less efficient ways of evaluating this sum for a given value. You should at least have a paragraph of text is how it is evaluated. I described that in point 1. Ask you did holdout, what was the degree of classifier you chose. Give a table of test errors for degree 2 to 7. Then 4 isn't meant to be a deep question. But I basically want you to come up with an answer to the following 3 sub-questions. When you build your digit classifier, maybe 1s are easier to recognize than 9s, or maybe 3s are easier to recognize than 7s. Based on your experiments, I want you to come up with some sort of opinion which digit is the easiest to recognize, which is the hardest to recognize, and provide some justification for it. There's more than one possible correct answer for A. B, I ask you which digits are most often confused. Why, I don't mean the why there's a little unclear. I don't mean a philosophical thing on why 7s are likely to be confused with 8s, but rather from the data, what's your justification in terms of the data. And then I ask you to, when you look at the test set, some of your digits you'll have gotten wrong. I ask you, relative to your algorithm, which are the digits that you think are the hardest to recognize for your algorithm? Probably they got it wrong. And then I ask you to also include the record number, i.e. where it came in the file, and a printout of the digit. That's just to give you a little intuition. When you go ahead and do this exercise, you'll find out some scanned-in digits don't look anything like the given digit, and presumably when you print that out to number 7, something which was hard to recognize, you'll get some very odd glyph that in no way looks like a 3, and it's just a little intuitive thing. Your source code. Then finally, on the back, I suggest, if you're going for the best possible report, to extend in some fashion. You can make up an extension. Otherwise, I give you some possible extensions. One would be to try Gaussian instead of a polynomial kernel. Another one is a slightly different update rather than the Perceptron update. Third one is coming up with a way of generalizing other than the method that we came up with, or using one from the literature. Another one is to use some SVM code or implement an SVM and compare it to an SVM, or choose some other algorithm of your choosing for this from, for instance, a neural network.
Excuse me, Mark, for those, is it necessary to code it from scratch, or can we use a library for those, just
No.
for sake of comparison?
No, you don't have to code it from scratch.
Okay.
Okay. So the second part you can do with somebody else, and I'll weight this more than the first four. I'll probably give it 40% weight, something like that.
So what part did you say? 40% weight?
Out of my 100%, I would normally weight this 20%, but I'll probably up it to no more than 40%.
That's the extension.
No, the whole assignment.
Oh, okay.
Okay. Questions? Yes.
If we do the second part in a pair with someone else, you said, do we both have to submit it?
No, you can submit only. So there's a little complication there. You only need to submit one report. However, when you submit that one report, be very clear, because sometimes I have trouble matching up who the person you've done the report with. So both of you make sure to say that so-and-so has the file with the reports in it. Okay? When you turn in assignments 3, 4, and 5, the printed versions to JJ, often when there's a group assignment, she has a special group sign-in thing. But I don't have any, quote, group sign-in for this. You'll turn in your package of assignments, I guess it's 4 and 5, as a single individual assignment, even though 5, somebody else will actually have your code or the report. You can turn in 2 copies of the report, but I'm only going to grade 1.
So the assignments are supposed to be submitted online and
the assignments are definitely supposed to be submitted. Yeah, they're going to be submitted both ways. I really only care about the code online. Okay, so submit the code online, but the printed assignment to JJ. I'll make an announcement to your email detailing on how to submit. Other questions? Okay. Yes?
Yes, maybe mention it, but the extensions, how are they going to be marked in terms of
I tend to mark the assignment as a whole. So, I haven't set out a specific 5% or 20% or 60% for the assignment. So if you have an extremely high quality, clear, correct assignment, you would probably get 85%. The extension is probably roughly 15%, but if your assignment is terrible in some way, but then the extension is very good, then the extension makes up for it, and kind of vice versa. Your main part of the assignment is more important than throwing in an extension. Okay, other questions? Okay. Okay, so now I want to go into Mathematica, but for those of you, I think I'm going to teach you very interesting things about Mathematica. But for those of you who want to work directly on assignments in lab, 406 is open, and Guangdong and Orlando will be there soon, if not now. So we'll take a 10-minute break and then jump into Mathematica.